All right, howdy folks. Welcome back to Professor Carbon. In this video, what we're going to do is go over the arrow pushing mechanism for the reaction shown below. And we're going to have a couple of twists and turns here from kind of a classic alkene addition. So the first thing I always encourage people to do when looking at a brand new arrow pushing mechanism is to take note of the kind of reagent. And the good news is elemental bromine, or Br2, is a reagent that we've seen used multiple times for alkene additions, and typically it does the 1,2 dibromination of an alkene. For those of you who have also studied the role that conjugation can play and the reactivity of dienes, you know you can undergo both the 1,2 and 1,4 addition of alkenes with that reagent. And that's good, because the next thing I encourage people to do with an arrow pushing mechanism is just to look at the starting material and the product and compare the bonds that are made and broken. And so in the starting material, we can recognize that we have a diene and then an alcohol. And so those are two important functional groups. And then in the product here, we've made a new carbon-oxygen bond. And by so doing, we've generated an ether, in this case, a cyclic ether. And we've clearly lost that double bond motif, and now we have an allylic bromide. And so more than a couple things have happened here, but let's just go ahead and start with the reactivity that we're familiar with, which is the addition of bromine across this double bond. Right off the bat now, we have kind of a challenging question here, which is which of these double bonds could bromine add across? And remember, for an arrow pushing mechanism, we're not necessarily asked right off the bat to come up with all of the possibilities. What we are asked to do, though, is to connect the starting material to the product with a reasonable arrow pushing mechanism. Because I can see in the product that the bromine ends up on that terminal carbon, I'm just going to start by making my bromonium ion out of that terminal double bond, because I think that that would be the most straightforward to generate the product that we're expected to draw an arrow pushing mechanism towards. So let's start with that. And remember, the alkene is going to attack bromine. Then we're going to need a bromine lone pair to come in and form the other carbon bromine bond. And that's the arrow I always forget, because I think that you really only need one from the alkene to whatever the electrophile is. But of course, the bromonium ion has two carbon bromine bonds, one from each side, and so we need an arrow making each of those two bonds. And so now we have that here. And then of course, the last arrow is the formation of bromide anion. So I'm just going to move this down a little bit. I have my bromonium. Now remember, in the normal alkene addition, bromine could come in and it could in principle attack via pathway A, or it could attack via pathway B. And typically pathway B would be better than A, because the bromonium ion tends to react at the more highly substituted carbon, because it has a greater percentage of positive charge at that more highly substituted carbon, because that carbon would be the one most willing to form a carbocation. Okay, in this case, though, we don't end up with a dibromide directly. What we have is this cyclic ether. And so what can happen here is now we can invoke this oxygen lone pair. And this in many ways should be reminiscent of a halohydrin formation. So if we just have a regular old alkene and we treat this with Br2 and water, hopefully what you'll recall is that we end up making the bromohydrin. And the water then attacks at the more highly substituted carbon, just like bromide anion would when opening up the bromonium ion. Okay, so what's a little bit weird about this, though, is we want to form a 5-membered ring. So 1, 2, 3, 4, 5, and that would mean attack on that alkene. We then could swing those electrons over and add those electrons up onto bromine. And so this would give us our cyclic ether, and then we would have bromine coming on out. We still have the H there. We still have Br minus floating around. And now we have this oxonium ion. This in principle could be deprotonated by HBr. For those of you who know how I feel about using bromide as the base, you can see the other videos. I would say realistically, an alcohol on an adjacent or neighboring molecule is probably really going to be the base there, or this may stay protonated until we actually do our aqueous workup. But in either case, that will directly give us our product and will generate HBr, which is the known product of this reaction. Now, this is kind of the key step here in blue, and this can be thought of as what is called an SN2 prime reaction, where that alcohol attacks through conjugation to open up the bromonium ion. If that's an SN2 prime, we could also think about an SN1-like pathway that I would also grade as being correct from an arrow pushing standpoint. And so I'm just going to put those arrows in red. What if this just opens up to give us that carbocation? And now we can draw a nice resonance structure with that carbocation. Oops. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6. Yep, forgot my carbon count there. Br, and then let's see here, we need a double bond here, and then the carbocation there. And so now we can have the attack, and that gets us to here. So this would be an SN1-like pathway. And for those of you that have evaluated this idea of thermodynamic versus kinetic products for the additions to alkenes, you know, sometimes it's not clear whether these are fully SN1-like or fully SN2-like. But in this particular case, if I were grading this in an exam, I would give students full credit for either the SN2 prime reaction to directly generate the THP ring, or if they want to open it to the carbocation, draw that resonance structure, and then to draw the alcohol attacking. That would be okay by me. Now, there's an extra little wrinkle down here, and it says the yield for this reaction is less than 100%. And that's almost always the case. Many of our synthetic reactions are not perfect reactions. And it's because many of them can indeed form byproducts. And in this particular question, we're asked to propose the structure of up to 3 possible byproducts. Geesh, not just one byproduct, 3 byproducts. Well, let's just go through our mechanism here, and let's consider what some of them might be. Well, you know, we made a bromonium ion. We have that bromonium. Oh, you know what? I spent a bunch of time talking about how that bromonium ion could attack via pathway A or B. And of course, if this is a diene, it could also attack over here as well. And so it could have the 1,4 or 1,2 dibromide from that alkene. So let's just draw those in. Those seem reasonable. 1, 2, 3, 4, 5, 6, 7. And then I can put a bromide on this end, and I can put a bromide on that end. Okay, and so that would be the 1,4 dibromide. 1, 2, 3, 4, 5, 6, 7. Put a bromide on the end, and then I could have the 1,2 dibromide. So that would be okay. And then let's see here. What else could we imagine going on? Well, we have a carbocation down here. And that carbocation could, I guess, be attacked by this alcohol. Now, that would be a little weird because there's a trans double bond there. But in the resonance structure over here, there is a single bond there. And of course, the resonance structure isn't going between double bond, single bond, double bond, single bond. The molecule overall exists as having a partial pi bond there. And that partial pi bond has a lower barrier to rotation than a double bond would. Higher than single, lower than double. And so we could imagine that flipping over. And so, you know, another possible byproduct here might be, instead of having a 5-membered ring, we could have a 7-membered ring and then have the double bond be in the ring. So I guess that would be okay too, by having the alcohol attack the other carbocation resonance structure. Now, taking it an even step further, which of these products could be converted to the desired product with extra time or heat? Ooh, that's a tough one. Let me see, which of these could go to, let's just draw out that desired product once more. So if that's what we're supposed to get, You know, this molecule looks like it could undergo an SN1 reaction to generate this, right? We could give off HBr, form that allylic carbocation, and then that allylic carbocation could be captured. This one could do the same thing. I mean, we could imagine that forming an allylic carbocation. It actually would be the exact same allylic carbocation that we get from the first molecule. And it would be the same allylic carbocation that we have up here. And so I think that that would be reasonable. And this last one looks like it would be the most stable, but of course, if we protonate this oxygen first by having it form a cation, then we've already studied the acid hydrolysis of ethers. And so in principle, that one could open up to the same allylic carbocation. So I think given enough time and energy, any of these molecules under strongly acidic conditions could in principle lead to the desired product. I will point out any of them that have a double bond remaining could potentially undergo a second dibromination as well, although the rate of that should be slowed down by the presence of the proximal electron withdrawing bromine atom. So that'll help reduce how reactive those alkenes are. But it's another thing to consider. Anyway, so there's actually a lot that can go wrong in this problem, but the good news is many of these intermediates may funnel to the desired product given enough time and energy. So I hopefully you've enjoyed this video from Professor Carbon. Please go ahead and subscribe to the YouTube channel. It's always fun watching that number tick up, even only a couple. And please tell your friends about it as a resource, as a reminder for those of you that might be new. All of the title slides are color-coded so you can find the content that you want to study, and you can find example problems that are relevant to what you're looking for. So pay attention to the color of the banner and then the kind of problem, which is color-coded up top. So that's all for this one. Thanks for tuning in.